because but anybody.
University of Rio de Janeiro. Okay, so yeah, welcome to the Ashok Maitra Memorial Lectures. We are delighted to have Professor Eulalia-Vares from Federal University of Rio de Janeiro. So she will talk about Ising and percolation under highly anisotropic scaling.
Thank you. Thank you very much. I'm very much honored for this invitation, and it's a big pleasure to participate in this series of lectures in memory of Ashok Maitra, a very important role for our area in this country. And reading about him, I learned we had something in common, related not so much in terms of subject we work, but in friendship with David Blackwell and Lester Dubis, were very big friends for me. I never worked with them, but so what I'm going to talk is, in this first part, is I decided to opt by starting something on statistical mechanics, because I see it as one of the biggest motivations for the development of probability in the last century, and stochastic process as well. So thinking that there is this initial part which should be introductory, I thought that there are students, and maybe it's good to start by describing a few keywords from statistical mechanics. So I selected three. The first are obviously necessary to be within any kind of keywords on statistical mechanics, gives measures and determines dynamic limits, and cuts potentials that might not be so known, but that's connected with the type of work that I want to talk about. So everything what I'm talking stays within the context of classical, nothing quantum statistical mechanics. Statistical mechanics aims at making this bridge between micro and macro descriptions of large systems, and as everyone knows or imagines, this naturally involves probability in a crucial manner. It is a branch which started long ago, let us say fathers of statistical mechanics maybe found in 19th century, started there. And it's well settled if you think of the description of systems in equilibrium. After the work of Dobrunshine, Lumford, Rel, mathematically is very well set in terms of this description in equilibrium. No equilibrium is another business. And so you have three giants in the beginning, Maxwell, Gibbs, and Boltzmann. And you have these three mathematicians, giants, Dobruch and Lamford-Ruel, who settled all this math. So Gibbs measures is to be taught as probability measures to describe systems in equilibrium in statistical mechanics. So here I put a photo of Gibbs and young Boltzmann. I like this photo that when he was young. So the measure connects both of them because you have the Gibbs measure, and there is the energy and the entropy, which was idea of Boltzmann essentially. So you have this well-known formula. So the measure of a configuration would be E minus a constant which is the inverse of temperature, and connects normalized, and so the entropy comes in naturally here. It's how many measures the amount of configurations that give this given energy. So it's a basic thing. So let us do a few quick examples. So the classical, the continuum, let us say the most, it could be thought to say the most important one, the classical one, which would be like you have a kinetic energy and a potential energy, and these guys are in the continuum, these momenta and positions, and so this potential should be repulsive at short distance and should be vanishing at a long distance, because should be attractive at long distance. So this is a part of where the issues of more sophisticated issues about phase transitions is still not so much done, as I will mention maybe. Then you go to much simpler models, which is called the lattice models. So including them, say, let's guess. So you simplify everything. You think of your space, the place where these molecules are, and in each place of this, each site or each vertex of a graph, if you want to think, you can have one molecule or not. So you have simply two possibilities, 0, 1. 0, it's empty. 1, that is a molecule sitting there, and there is only one. You cannot have more than one. And then you have an energy, which you describe like that, in the sense that there is an interaction which connects what is in I and what is in J. So when this J is positive, so you have a minus here, that means you make things attractive. And okay, you have some, and it's very common to change from 0, 1 to minus 1, 1, because we are thinking of magnets. Instead of saying that there is a molecule or not, we think that there is a little spin, and this spin could have two orientations, and then we call what is called the Ising models for magnets. So it's the same thing, you just replace 0, 1 by minus 1, 1. And I'm here describing the simplest one, where this J is constant J if the distance is 1, so only nearest neighbor, it's a local interaction, and is 0 otherwise. And there might be a magnetic field, that means, so this energy tends to be small if these guys agree, because when they agree this becomes a plus, and then since there is a minus and J is positive, this decreases the energy, that means increases the probability, because in the measure you have E minus J. And here the same, the sigma would like to agree with the H, if H is positive or negative. So you have just writing what would be the energy, or Hamiltonian sometimes called, in some few examples. And the option for your probability space, your sample space, depends on what you want. So sometimes you want to fix some observable, so you want to look all configurations with a given energy, all configurations with a given density, or sometimes you don't want to fix anything, it just has the temperature on it, which is given by the beta. So this is called the values ensemble, or was the name used by Gibbs. Microcanonical, when you fix canonical, this you fix the energy, this you fix something, and grand canonical, which is when you don't fix. And the good thing is that for the math, since after the math which has been developed, you have the notion of equivalence of ensembles, in the sense that you can deduce properties of canonical, microcanonical from the grand canonical. That means you can write everything in terms of a given pressure which is obtained in the grand canonical setup. So these are just the basic concepts which are not essential for what we are going to do, but just to... let me go to a trivial model, which is nothing at all, it doesn't have a, it cannot be taught as reasonable from the physical side, but it's very important to indicate roads. It's a kind of a laboratory model, which is the mean field or the Curie-Weiss model. What is in this model, you think that everybody interacts with everybody in the same way, which is not reasonable, of course, but it is okay to make it, this assumption. So you have a J, since you want the sum to be, the J has to depend on your volume, so which is maybe not reasonable, but it is the way it goes. So J is a constant in the way that when you make your computation here, it becomes trivial because the energy is a function of only one variable, which is, say, the sum of the sigmas or the density, if you want, the average. Now, because you just write this and becomes the sum squared divided by 2, the size of the volume, how many molecules you have or how many spins you have, some small error here because of the diagonal. And since it is a function, it depends only on one variable, it's just a one-dimensional stuff, it's very simple. And you can see right away how to compute things, because the normalization is just you have to count how many sigmas have a certain sum. So how many of those configurations with n plus or minus have a given sum. So this is simply obtained by combinatorial, so Stirling formula will give you that in the limit everything is described by this. So you look at this function, so this would be like the free energy function, or if you want to think, the rate function. So your function, your measure at the end would be it minus f. So you see that this, just by computing, looking at this function, computing how it looks like, and looking at the critical points, you see that you have a sort of phase transition when beta is 1. It's as the n, which is, say, the number of atoms or molecules go to infinity, the size of there is a sort of a trivial phase transition, in the sense that if you look at the behavior of the average, because everything is given in terms of the average, it has a different behavior when you go from beta less than beta critical to beta bigger than beta critical. When it's smaller, you have a Gaussian centered 0. When it is bigger, then you have a mixture of two Gaussians at the two guys which minimize this free energy function, which are the two solutions of this equation. If beta is larger than 1, this equation has two solutions, plus m beta and minus m beta. So you have these two guys, and it will be concentrated, it will be a mixture of these two, which means that you would have a free energy, which is a double well, with the two wells sitting at these guys. And that is, of course, a free energy is something which has to be convex. And this is not. But it's not because we have a model which is not reasonable from a physical side. It's just mathematically nice. No? So, but it's very important. Why I'm talking about this model, because it will be very important for what I'm going to say afterwards, which is how to give something more reasonable physically out of this model. I mean, mathematically, there are many nice things that can be done about this model. Okay, but it is the key word here is that there is one example at least that allows this trivial phase transition that can be precisely computed. But it's not very clear what does it mean. That's why I put it quotation marks. So the other key word is the thermodynamic limit. So this is extremely important because you want to take your volume lambda to grow, because you want to make a connection between micro and macro. In macro, this volume has to grow because the number of molecules is very large in your system. Okay? So what you hope is to find a relation between the thermodynamics, and that's why statistical mechanics was important when it was created, to discover the relation between what was already described by thermodynamics as principles with your system, with the microscopic description of your system, with the behavior of your observables. For instance, the density, the magnetization, which are kind of the same depending on the interpretation, and the pressure. So mathematically, we think that phase transition means that you have more than one Gibbs measure when the volume tends to infinity. So what does it mean? That the local descriptions, how the molecules interact with each other, how the spins interact locally, is not enough to determine a unique measure. No? The influence from the infinite is present depending on the temperature. That's what does it mean, whether it means this phase transition. There is, in terms of DLR measures, that means if you take a boundary of your volume, and depending on the temperature, different boundary conditions will give different limits. So in terms of, there is more than one DLR measure in the limit. So these measures, which were fixed when you take a lambda, now you add interaction with the outside, and you make a lambda grow, this might have more than one limit. So this is the notion of phase transition in terms of statistical mechanics. And the important things here are, say, this became, of course, extremely important subject. So the first model, that's why I mentioned the Ising model, was the Ising-Lenz model. So this was in the thesis of Ising when he was a student in 1925. But he was looking at D equal 1. So in dimension 1, this is a Markov chain. So in a Markov chain, we know that is a unique measure, defines a unique measure. So he found no phase transition and conjectured that maybe this is going to happen all the time. So he went to do something else, but in 36, Rudolf Peierls proved that you have a phase transition in dimension bigger or equal than 2. In the sense that for low temperature, that means beta is large enough, you have influence from infinite coming to the origin. So and you might have more than one measure. So this became, this model became very important. It's, I don't know how many papers, how many citations involving the name of Ising, but he himself was not working on this. But it's extremely important. And which was the key tool to show that? if you want to see that there is an influence, now depending on the value of beta, if you have plus, say, let us say in the spins, you have plus and minus. If you have plus outside, it pays what it pays to have a minus in the origin is different than if beta is small. So there might be two measures. In the sense that if you, and this is done by the consideration of what's the price that you pay to have you have a region with minus separated from a region with pluses, say. You have the notion of a contour. What's the price of a contour? No? And this argument of Peyer's, what became known as Peyer's argument, is the key tool to show that there is no unique Gibbs measure. And it stays. So it's basically, as we can see, it's an idea of percolation, that the influence from infinite reaches zero, the origin or not. That means to have a minus in the origin when I have a plus very far, it's very different depending on the value of beta. So that's a key tool that will be used also for our, so you want to say that if you have this price as, what you want to say that the influence from infinity reaches the origin in the sense that you see something different according to what you put at infinity, that means you need to estimate the cost of a contour. And that's basically, it can be seen like this. It can be seen a question of percolation, that the cluster from the origin reaches infinity and vice versa. So that's something which we are going to use in a different model in the main part. The other keyword was Katz potential. So here is a photo of my cats. So what was the key role of Katz potential was to be able to find a relation between statistical mechanics, rigorous statistical mechanics, and this description which we saw about the Curie-Weiss, that there is this trivial phase transition, that you have this non-convex free energy, which is a strange thing, which shouldn't occur. So, and so that played a very important role for that. So let me try to say a little bit why. So what Katz did was, well, let us say, besides our interaction, let us put another scale. So we add a parameter, gamma, which doesn't have dimensions, just a scale parameter, and we scale the interaction with the gamma. So beside we had a j, now j, the interaction between x and y is scaled according to gamma, in the sense that we think of gamma as going to 0. So x and y interact well if they are not too far. They are within 1 over gamma, let us say. And this is weighted in such a way that this becomes integral, let us say. So what did they do? Katz, Uhlenbeck, and Hammer in the early 60s of 20th century, they proved that if you fix this gamma, look at what one does in statistical mechanics. That means you take the thermodynamic limit, okay, and that will get something that involves gamma. But afterwards, you send gamma to 0 afterwards, then you recover something very important for thermodynamics. That means you will explain the van der Waals-Maxwell theory, which was sort of mysterious. What is that? Well, if you just look at the isotherms of van der Waals, so here is, in this axis, V, specific volume, which means 1 over the density. So when V increases, density is decreasing. And here is pressure. So this is something just based on thermodynamics. And you just write down the isotherms. So the curves where temperature is constant. So when temperature is large, it's these nice curves like that. So there is a critical temperature where you get this behavior. So there will be a piece of your isotherm where the density is decreasing and the pressure is increasing. We don't need to know much physics to see that this does make sense physically, because the density is decreasing and the pressure is increasing. No, something is wrong. So, and this was, something just invented by van der Waals, starting from the ideal gas equation and make some simple restrictions that there is molecules cannot be too close together, and they are okay. So there is the important thing is that this Katz's potential allowed us to explain this, related this to statistical mechanics. And what was it? Maxwell. That's why this is not only van der Waals, but van der Waals-Maxwell. When they had this, you have this non-physical behavior, Maxwell said, well, I mean, the rule should be, the correct thing should be that you hear it's constant, and this constant, where do I locate it? This is at the point where the area here is equal to the area down there. And this argument, it's the same, it's this one, and now you put the Maxwell rule, which means that the true should be this graph here, and a line. Where is it located? At the point where this area is equal to this area.
What is the y-axis?
The y-axis pressure. And here is 1 over density, specific volume. So it should be constant. Because, of course, the mistake of this argument of thermodynamics is to think that everything is homogeneous. What is not homogeneous. When there is a phase transition, something is changing from liquid to vapor. There is a part which is still vapor and a part which is liquid. The same when it's getting changed in liquid to solid. A part is still, so it cannot be treated as everybody is in the same situation. And the argument of Maxwell here was based on some mechanical argument in some sense. So what is important is that Katz's potential allowed to get this out of statistical mechanics, so out of a rigorous argument of statistical mechanics. And how is it? Because this theorem here, which is in the original paper by Katz, Uhlenbeck, and Hammer, says that the true free energy, that when you make this double limit, you take the limit, thermodynamic limit, of the free energy. Just look at the free energy, and then take gamma to 0. What you get is the convex envelope of the, so you get a convex function, which is the convex envelope of what was Curie-Weiss. So, and this corresponds exactly to have this Maxwell rule. So it had a very important role in this sense, that connects something which was not at all statistical mechanics, which is thermodynamics, with statistical mechanics, allows to give a formal explanation of this rule. And this was extended by Lebowitz and Penrose to to a large class of systems, and it's called the Lebowitz-Penrose approach. But let me, before I enter to, so the important thing is this. So what was the, if you look at the system, in this, some interaction system in statistical mechanics, so you have your potential J, and everything is well defined, so you have a free energy. This has to be convex, and the pressure is convex, and pressure is the Legendre transform of F, and conversely. So this is, what is important is that they proved that if you make this for a given gamma, and then you send gamma to 0, you recover the convex envelope of what was in the trivial Curie-Weiss model. So in this sense, it is, so it was a very important role as a connection between thermodynamics and statistical mechanics. So that's what I try to explain. So you have something which is not a proper interaction because the J depends on lambda. So you cannot make lambda tend to infinity with this J. No, you made a computation of the free energy, of the measure even. And so what they proved was exactly that. That's the main thing. But this was in the early 60s, and it stayed, nobody was doing anything with Katz's potential. As far as you can go in the literature and see that there was sort of sleepy for a while. And in the 90s, there was a very important revival of this subject because you could do much more. No, because everything, what was done was very little. It was just in terms of thermodynamics. You take the free energy, sorry. And then you might ask many other questions, which brought not only very impressive progress to the field, but also brought many important mathematical questions related to variational problems. And this was in the 90s. And among the questions, you may ask, okay, so what happens, suppose you have a model like that your beta, suppose you, let us do an interaction like the Curie-Weiss. Suppose your beta is bigger than 1. That means in a mean field regime, you have a phase transition in that sense, that you have this double well. Can you find, now fix that interaction, which is, say, 1 if they are within 1 over gamma, and 0 otherwise. And you ask the following, can you find a gamma? No, given a gamma is small, can you find a beta that for which you have phase transition? That means if temperature beta is larger than beta critical, it depends on gamma, you have, so that's the question. You take any beta bigger than beta critical of mean field, can you find a phase transition if gamma is small enough? That was, it's an extremely important question, and it was addressed in the 90s by two groups of authors, by Marcio Cassandra and Enrico Perzutti, and by Anton Bouvier and Milos Zaladny. So this brought a very important thing, not only because of the result itself, but because of the techniques that have to be developed. Because you want to look at the interaction with a gamma, which is very small. So this interaction is the one that I had mentioned here before. Now it depends on gamma. So whatever you have to do, it must involve some coarse-grained description. You cannot, your contours cannot be just this spin with this spin, then I put I made the contour just by spins. No, it will have, because the interaction will take into account what happens in a certain region, of size 1 over gamma. So it brought a class of very important questions involving this description in an intermediate region, intermediate scale, with, let us say, it's not microscopic, neither the final macroscopic, it's mesoscopic description. And instead of looking just a free energy function, now you have to look at functional, because you cannot consider only things which are constant. You need to take a profile of your magnetization, of your density, and look at the functional as a function of this function. So the variational things involved there are extremely interesting, also from a purely analytical side. So that was important. And this, I think one of their motivations also is that the progress regarding phase transition for models in the continuum is still not so big, but they were able to make progress showing phase transition in the continuum, and that's probably very few papers doing that.
So when you do the contour argument, are you sticking only to 2 dimensions or in 3 dimensions also?
Also in 3 dimensions.
So how do you define only contour, so to say?
They,
It's a larger 2 dimension, right?
no, you can do it in 3 dimensions. The same also for Ising model. You might also do it in 3 dimensions. But already in 2 dimensions is interesting equally. But we can discuss the details, how the contour, because this, the matter of the dimension is not too important. I mean, dimension 2 or 3, the idea is the same. The difference is not so much in the dimension, but it's the fact that you need things are coarse-grained. So you need to introduce, you cannot just measure the spin, so how you evaluate them. So, but the question of the dimension is not so, doesn't change too much from, say, the usual Ising model to Ising with cuts, if you do dimension 2 or 3. Of course, technically is more involved to look at. So that's why when we have to prove something in 3 dimensions, instead of looking directly, we try to use some inequalities or things like that. Another thing which I consider particularly important here has to do with because let's go back here to this picture here. So you have this which is not reasonable, no? Maybe I show in the other one. So this part here is completely meaningless physically for anyone, but there is this part which makes sense. It doesn't contradict any basics of physics. No, this part here. What's the interpretation of this part? So this is connected with the possibility of metastable. No, that means instead of undergoing the transition, say, from liquid to vapor, part of the system stays still in liquid, or the other way around, this size or this one. And that could be this branch has a connection with that. So there is an important development here, and there was all these proposals how to describe metastability from this side, in this direction, no, as if it were a sort of equilibrium state, though it is mostly dynamic. But anyway, there was all this proposal to say some analytical continuation of the energy, and what one could see exploiting the Katz potential is that though you don't have analytical continuation, you have, as you take gamma going to 0, you have more and more derivatives which match to what you to that metastable branch. So it appears naturally in this way also. So that's an important clarification of this metastable branch in the van der Waals theory, now because he called this metastable branch, and it appears naturally, or naturally, no, it appears mathematically when you do the limit, Katz's limit. So Katz's limit played an important role, so this is a kind of propaganda of Katz's potentials. Now I want to go to my model. Okay, so the model which I want to talk is the following. You think of easy spins on the plane. On each line, they interact as a Katz's potential. So you can say that J here is a nice thing with support. Now this function J is support, say, -1, 1, and integrates 1. It's a probability kernel. And so the spins interact according to a Katz's potential given by this J. So spins at I and J, they interact if I minus J is less than 1 over gamma. Okay, so that's a nice interaction, which is connected, of course, with the Curie-Weiss. But it's now a true interaction all over the volume. So this is just one-dimensional Katz's potential. So in one dimension, of course, you don't have a phase transition for any finite gamma. You just have this mean field phase transition that when beta is larger than 1, then you have this double well structure. So that's what it happens on each layer. Now, vertically, I just add a small nearest neighbor interaction. And so if I have an easy interaction, which is interaction is just, I call it epsilon. So it's been sitting at a certain site and sitting on the top of it, they interact as a very small easy interaction. So this is epsilon. So that's the model.
So when you say interaction, the Hamiltonian is what?
Yeah, this is the J. Exactly. Okay. So we asked the same question that Cassandro Presutti. Do we have a phase transition? Say, no, I am considering here in this situation. Here I didn't write that, so I wrote probably here. So I want to ask the following. Given beta bigger than 1, I shouldn't write there, but it's written in the theory, but it's, or bigger or equal at least than 1, and epsilon. Let us think that I am calling mu plus and mu minus of gamma the DLR measures with boundary conditions plus or minus. Now there is a limiting measure because of general facts. So these thermodynamic limits of the Gibbs measure in a finite volume with boundary conditions plus or minus. So you can think outside a certain volume, I have only pluses. So, and when I make this volume grow, then there is a limiting measure. And this limiting measure I call mu plus gamma. It depends on my gamma. Gamma is fixed first. And you ask the following. Is it true that for any epsilon that I give, I find 2 measures, that mu plus is different than mu minus? Do I have phase transition? So that's a question which you might think at first that it looks a bit crazy, but it's not. So the theorem which we can prove, and that's work with Luis Renato Fontes from São Paulo, Domingos Marchetti, also from São Paulo in Brazil, Immacolata Merola from Rome, and Enrico Presutti from Rome. So what we proved was that, well, for any beta which is larger than mean field critical beta, you can make epsilon any power of gamma, and still you have these two measures are different. The magnetization will be one of them in the limit gamma is will be m beta, and in the other will be minus m beta, as imagined, as it would be natural to think. That's one thing. And now when beta is equal to 1, if beta is equal to 1, there is not m beta is 0, because there is only one solution of the equation. M beta equal to tangent, hyperbolic tangent of m beta. But still, any epsilon positive, but here I'm taking epsilon fixed, not as small as this. I have the two measures which are small, different for gamma small. All of them are for gamma small. You might think, why am I interested in this? Well, our motivation was mathematical because this poses challenges with respect to what was known for two-dimension, because the interaction is on the vertical is too small, and you cannot use the tools of two-dimensional Katz potential, neither the tool of just the easy mode. So our interaction, but you can think that there are many places where these interactions being very, very kind of extended and it's like sort of Katz interaction in one direction, and very sharp and local in the other direction happens. Like if you have, of course, they are not interested in this one because that's, if you go to atomic level, it's another type of stuff. But anyway, but you can think that if you have these very thin things of graphite or graphene, then it looks like this kind of thing. And you find a lot of this in the literature in physics in this direction, when they have these layers which are just two layers of something, where the interaction in this direction is very different than in this one. But of course, they are not interested in Ising models, but it is. So.
Can you show the interaction again, the way it is defined? So
In one line is like Katz, one dimensional, and in the other one is nearest neighbor.
Okay.
And where does the beta come in the Hamiltonian?
The beta is because the beta is not in the Hamiltonian, it's in the measure. It's the inverse temperature. It's e to the minus beta h. In h is the one which has the Hamiltonian.
And gamma also in Hamiltonian.
Huh?
Gamma also in Hamiltonian.
Yes, yes, gamma is in h. Yeah. H, that's why I had the h and the j. H is in the j. H is minus the sum of the j's, sigma I, sigma j is the h. In the per,
One line is for every x is over one line.
yeah, this is on each line I have this interaction. Here the second coordinate is the same. So when I am on the same, and when it's not the same, I have epsilon. So I have the sum, the whole Hamiltonian is the sum of this in x, sum neither Hamiltonian, and here also. But this is just formal because I cannot sum.
So should we consider where epsilon is more than non-zero? Should we consider it between somewhere between a one-dimensional and two-dimensional problem? Is that the correct way?
Sum between?
If the epsilon was
The epsilon is fixed, yeah.
so
Here is fixed.
So let's say if epsilon was strictly zero, then we will have a one-dimensional series of chains.
Yeah, I would
Which
have
have
just one independent. If epsilon were 0, I would have one independent one-dimensional systems.
Yeah, and if epsilon was reasonably large, of the order of the CAC interaction, then you will have an effectively two-dimensional problem, right? I mean,
If epsilon were, say, 1 over gamma,
Yeah.
somehow.
right,
Yeah.
yeah.
But it's not, it's fixed, and gamma is going to 0.
Gamma
So
is
this interaction is too small in order to
Have
use a
any-
two-dimensional, yeah. So that's the kind of thing which I want to discuss a bit now. And maybe it's exactly answering your question. So the first idea that one think, can we use the approach that Cassandro Presutti and Bouvier-Zaradnik use? Can we think in terms of Lebowitz functional for the plane and use this? And it doesn't work because the vertical interaction is too small. Okay, so the vertical interaction is too small. So we need to do something else. But say for part A, the idea is simple because since beta, if beta is larger than 1, and you just look one-dimensional system, it's of course there is only one measure. But how this measure looks like, it will have long strips where if you look at local magnetization, say of scale gamma, 1 over gamma, it will be very close to plus m beta. And after a very long piece of this, it will change to minus m beta. So it will have plus m beta, then minus m beta, and so on and so on. So
basically create domains of magnetization as we say.
yeah, in some sense. Yeah, exactly. So you believe that putting one of these and interacting with another one might allow you to show some transition in case, because you pay to have one of plus and one of minus here. For each one you pay little, but since there are too many, maybe you can get that one. So that's the main thing is how much you pay for contiguous layers. But in order to do that, I went too slow in the beginning, so now I'm running out of time. So I need to. The main idea to which I wanted to comment to use in Katz interaction is the use of coarse-grained procedures. So you need, and this usually involves 3 scales. Say one scale, I put 2 here, but in fact 3. One scale is smaller than the interaction length. So interaction length is 1 over gamma, is L minus, and one which is bigger. They much bigger. No? So, and you look local averages of your magnetization of the smaller scale. So I'm just looking, and I split my interval, my line, into intervals of length L minus. And if I do this coarse grain stuff, maybe in one interval I have average very close to m beta. Then I declare this interval to be a plus. And if it's very close to minus m beta, I declare it to be a minus. This is the variable feature. But maybe it's neither one, neither the other. So I am undecided. Then I put a 0. And you do something similar when you have a bigger scale, but then you need to look a bigger scale. All those of the previous scale are plus, then you declare it to be a plus. Otherwise, if all those are close to minus, you declare it to be a minus. Otherwise, you don't know, undetermined. So there is a lot of undetermination, of course. It's coarse-grained. But now we want the vertical ones. So I'm going to declare it this big theta that I am in the to be a plus. Now when I have all these pluses, also in the top layer and in the layer down. That means I am, if I look at this box here, I am in a phase plus, in the sense that I look everywhere and I am plus in this sense. You know, everything is coarse-grained. So now, and you would like to use these variables for your Pyre's contours. So the notion of a contour, I need to be fast now because I went too slow. So what was before just you have spins plus, spin minus, now it becomes something more involved. But each square here represents a line where you have all these guys, all these smaller intervals are plus. So I put a plus. When I have a 0, means that I am undecided. So the notion of a contour is more involved now, but it has to be. No, but you have something. So, and you can say if you have a plus contour when there is a bounded region, so the outside is plus, then you declare that you have a plus contour, and you want to say the price of the contour, because you want a kind of Peirce argument. And what we are going to use as a fundamental thing to prove is that how much you pay to have a stripe. A stripe is something like that. You have many pluses, and below you have many minuses, these blue pieces. And then when you do the estimate for that, the same idea used for in general in Peirce argument, you need to estimate how much it costs to have something with the contour, the price of a contour. No? And the estimate which we can prove is that you will see here that I have a plus contour, so that means outside my region I have pluses, and I want to estimate what's the price of this W. So it's the analogous of, so it's the partition function restricted to this contour, no? Divided by the partition function when it's not present. And you see here that there is the contribution of these stripes. That means when I have these blue pieces, I have many pluses and many minuses, or the other way around. It's coming here as fundamental thing. Oops. Oops. Well, it's not coming. It's coming here as fundamental. Then whenever, after you eliminate all those stripes, you get something like, more or less like as a one-dimensional easy model. Then you can prove this estimate. And of course, once you have this estimate, then there is an entropy, like the same counting argument for once you have the estimate of the contour, you have an entropy to do. How many possibilities you have to have this contour around containing 0. And that's coming in this second, but this is like a kind of quite a general argument. Unfortunately, I think I will have no time to discuss the second part, the second theorem, which is epsilon is fixed. But let me, how many minutes do I have? 3? 5. Okay, so let me just say, this is the case where beta is 1. So I don't have m beta, it's 0. And what can I do? But I have an epsilon, which is fixed. And what we could do is the following. Well, if you have 2 lines, one is able to find some m beta positive. But the point is that I cannot just group my things in terms of the line 0, line 1, then I skip the other, because there is an interaction everywhere in vertical. So what we did was the following. Let me go to this. We changed first our Hamiltonian to something which we delete some vertical interactions. So all those which are in gray are deleted. And I have this guy. And the horizontal interactions are as before, everywhere. But the vertical interactions, they are only when there is not a gray. And by doing that, if we can prove phase transition for this, we can prove in the other one by general correlation inequalities, because everything is ferromagnetic. So the GKS inequality. Griffiths Kelly-Sherman inequality allows to do. In order to do that, there is a lot of, a bit of work, but one can do. And let me go back to resume how we can do. First, we need to look at the mean field free energy of two layers and figure out that there is an M epsilon that comes out. That's not too difficult. Basically, you have a chain of independent pairs, and you get this M epsilon. Once you get this M epsilon, you want to use it to define the contours. The contours are defined with respect to some value, in this case, M epsilon. And we do it more or less as if we were in the one-dimensional system. But now we need to find to implement a proper coarse-grained procedure for this more complicated stuff. And it requires making a true two-dimensional thing. And in order to do that, of course, I have to define these coarse-grained spins. And but it has to be two-dimensional. So what we do is all these guys are defined. What becomes my new spin, it would be some pieces which have a certain number of layers and like that. No? So there is always a small difference here because I skipped some, that there's no vertical interaction. And for those guys, we kind of need to redo, but it has to be done afresh in the sense, but the same ideas that were used for the two-dimensional Katz model by Bouvier-Zaradnik, by Cassandro and Presutti, but for these spins. And doing that, one is, it's a bit messy, but one is able to prove. And the point is that we were not able to do here the fully system, and that's why our M epsilon is a bit smaller than what it can be. Because I am running out of time, so I don't spend time on the details. I just go to the end. So these people here, Cassandro, Colangeli, and Presutti, they were able to do a Lebowitz-Penrose system for the original system, ignoring these gray pieces. It's something which uses a lot of cluster expansions, and as outcome, they get the square root of 6 epsilon. Ours is smaller because, of course, we are neglecting some interactions. And, but you see that our argument, as well as theirs, has a problem that you cannot make any anti-ferromagnetic interaction somewhere. It spoils everything because we, when doing this chessboard stuff, we left some pieces. And then if you put something anti-ferromagnetic, we are lost because we use correlation inequalities. An interesting question related to these models is if we were in higher dimensions, instead of having just 2 dimensions, here where the plane, say, we are in 3 dimensions, and everything goes. But there is a question which is very interesting, is for D large and beta large, can we find Dobrushin states? That we don't know. And the other question is, for the last part where we had this epsilon which was fixed, can we find the epsilon, can we find a B such that if epsilon were of the form gamma to the B, we would see a change in behavior. We would see a change in behavior as we change this kappa, in the sense that B would be sort of a critical scaling for this, in this sense, that there would be a universal constant such that if kappa is less than the universal constant, you have a unique measure. If kappa is larger, you have more than one. We are not able to do that for the Ising model so far. It's an interesting question. We are able to do only for the percolation. And that's what I'm going to talk in the next part. So it doesn't use anything of Ising, it's just a percolation construction. But it's motivated by this question. Sorry for I was a bit late. Thank you very much.
Any more questions?
I have a question regarding this continuous model you said, model in continuum. Can you maybe, even for the last, is anything known of any continuum models?
I think the only thing which is known for the continuous model is when you have, it's this paper of Lebowitz-Penrose, Lebowitz, Mazel, and Presutti, and I don't think there is anything so much beyond that.
Thanks.
And it's, there is a drawback in that one, that they need to take also Katz's interaction in the repulsive part, which is not so much. But they use, that is, I think it's well explained in the book of Enrico Presutti. In the papers, of course, also, but also in the book. In fact, maybe your question allows me to say there is something common in all this reference, which I put it here, which is Enrico Presutti. I think it's due to his efforts and his work that there is a lot has to do with this revival of Katz's potential and all these ideas of coarse graining and variational problems connected with statistical mechanics for these systems. And then, in fact, since he is a mentor for many of us and had a very important role in probability in Brazil also, and not only in interacting particle systems, for his 80th birthday, we made a volume of a journal that I want to make advertised, which is of the Brazilian Mathematical Society, and which I invite everyone to, whenever they feel like writing a survey. It's mostly concerned with surveys that allow students to enter a new subject. So we wrote one which is a series of papers in honor of Enrico Presutti. And so it's online, free, this journal, but I have a copy of this special volume that I leave here to make...
Okay, so we'll meet in 10 minutes, 3:15.
Thank you. I can go? Yeah, okay. So what I'm talking now is motivated by the previous theorem, but it's totally independent. So it's about the same question, but in the case of percolation, which is easier. So since thinking of the students, let me say a few words about just motivation of percolation in general. So this is something which started, mathematical modeling started with Simon Brobet and John Hammersley. They invented this famous model to study connectivity of networks. A bit before, it's good to say something about history. So there is important to mention experimental work, which was already not so crude, let us say. And an important name is Rosalind Franklin. She, though of course she is famous for other things, but there was a series of works of her at this center here in the 40s, so before them. And she was working on more experimental things with carbono and doing that. So it's, I like to mention that this was done a bit before. There were other, but this was sort of, if you go to see this material, it's a lot of computations, a lot of data, so it was quite quantitative. That's why I'm thinking. So they want, so the more classical model is this. You just, to each edge of Z2, you toss a coin. If it is head, you open the edge. If it's closed, you close the edge, and you do this independently. So this is the Bernoulli percolation model, so the Bernoulli measure to the edges of Z2. Other classical ones, you just take n vertices, and you, for each pair of them, you put a connection or not according to a coin tossing. With this independent coin tossing with a probability p, you have this graph, which is called the Erdős-Rényi model. So it has two parameters, and the number of vertices, and p, which is the probability to put a connection between them. So this plays a role for this stuff that we are discussing, somehow similar to the Curie-Weiss model for the other one. Okay? So, and though it's not necessary for what we are going to do, it's important to just recall this fact here, which is very interesting. So you now think that you have your P going to 0 at the same time that n's go to infinity. It goes to 0 like that. Constant divided by n. Huh? And so there is a very nice phase transition. It's similar to what we had seen at beta, but here it's much more is known, no? In terms of much more is taught. If lambda is large, then you have one component which is very big. It's of the order of the volume, a constant part of the volume, and all the others are very small. If lambda is less than 1, everything is small. All the components are very small, the connected components. And around 1, you have a very interesting behavior. Around 1 is around criticality. So, and this was proved by Aldous and Martin Leff at the same time, independently. So if you take P just around 1 over n, in this way, then you look at the component size. They have this n over n to the 2/3, and they converge in law to something which is well described by them as multiplicative coalescence. So these are described in terms of excursions of reflecting Brownian motion, which has a drift which depends on time. But in a more compact language, let us say it's called the multiplicative coalescent. We don't need that, but it's just to mention that there is this very interesting behavior around 1. So what we want to study is this percolation model, which is anisotropic, motivated by what I said before. So you have on Z2, you have vertex, which are just the points of Z2, and edges, you have 2 types of edges. The horizontal edges, they have length from 1 up to n. N is my parameter, it's the 1 over gamma, which I had before. And the vertical ones, they are just nearest neighbors. Okay? So it's just that. So you have, in the horizontal, you have long edges, but length is fixed, long, but up to n. And the vertical is just small. And then you think that the horizontal edges are open with the probability 1 over 2n, because there are 2n edges. So this is critical, as if I locate myself at 1. And the vertical edges are open with a small probability. It's a kappa times n minus b. So this is exactly the gamma b which I had before in the vertical edges. No? So this is the model, and you ask about percolation. And so this is just saying, if you want to, since this is, if I think of only horizontal, say I cannot move to the other city, I am restricted to travel only within this city, then I think that I have this critical behavior, 1 over, okay? And then you can imagine of making a dynamical construction, which you just, you know, initially it's similar to branching random walk. You put the edges, now you throw how many guys you have, but on the average it's just 1, and you keep putting these errors, then sometimes you come to a place where you already had been, so it's useless, and you can construct this like that. And the question is connected, no? Given a B, which is the B for which I find a transition in kappa. So, and we can prove that B is 2/5 in this sense, that you can find universal constants, C1 and C2, such that if kappa is less than C1, there is no percolation. If kappa is bigger than C2, there is percolation. Where to have percolation means to have an infinite component. There is a positive probability that the component of the origin is infinite. So let me just show some, just to illustrate, especially because of the students, to show some simulation, just to illustrate. Oops. What's happening here? So it is a model where it's more spread in the horizontal, but it grows vertically, and so on. Just to give a flavor. Now I think I have a second one which is more successful. So you see how it grows. So there was this big hole, but now all of a sudden it came back, and then it spread it again, and that's it. I don't think we need much more than that. Just to... in the proof I'm going to use several starting points, but you see that this is just illustration, so I think I can stop. Okay, so this is the model that I want to study. I think its study brought some different subjects in contact, so I think it's nice because of this. So the motivation I don't need to describe now because we just heard about it, so I forget. We don't know to answer how to answer that conjecture, which was the same question, but for the easy model. But if you want to go from this to this one, we can answer. In terms of percolation, the phase transition for the easy model would be a question of percolation for a model, but the measure is not a product measure. So it's more involved. It's the so-called Fortuyn-Castelline measure, which you would have these probabilities looking like the same ones that we have, no? The same behavior, because they are just given by that. So when this is small, so this is approximation is in the same order, this also would be the epsilon approximate. But the measure is very different in the sense that it's Hadron-Nikodym derivative with respect to the Bernoulli measure. It's Q, which is in this case is 2, just because Ising has only 2 kinds of spins, to the number of components that you have. So it's, I don't know how to answer the result for the for this measure. Okay. So we go to the original question, which is just for the simple percolation model. Can we prove that 2/5 has this behavior that we mentioned? So the main point, in order, at least the way we look at that, but I guess it's.
One question: is there any simple way to guess the exponent of that p value?
This 2/5?
Yeah.
Yeah, it is simple, but in the first guess we did it wrong. Because for the easy model, our first guess was 2/3. And the fact that for this one is 2/5 shows that it cannot be 2/3. So when I get to some point, it will be clear why 1/5. But at the moment, it's not so clear how to tell that I tell you in 2 minutes, in 1 minute. But at some moment, it will be. I hope it will be clear why it has to be 2/5. But it's not so. And the fact that we did a mistake in conjecturing for the Ising shows that, or it was wrong with our intuition, or it was not. But here it's easier than in the. Okay. So, and exactly, to get to this 2/5, the important thing is to understand very well how it is the cluster of the origin when I connect only restricted to its layer. So it's somehow, it's not the same model as I had before, because that was n vertices. Here I have on the line, but each one can connect up to n. And you want to know how it looks, this connected component for restricted to the line. Once one understands how it looks well, I think the 2/5 emerges. Okay, so that's what we want to. Okay, and you think, well, this component, I can think that I constructed it dynamically. So I start with the origin, I have its children, then I have children from the children, children from the children, like a branching. Of course, the branching is much bigger, because the branching might have many people. Branching random walk might have many people on the place, and also can visit again the place which has already been visited. So we want to compare this process, which is, I'm going to call C hat K, these generations of this evolution, starting, this. So this C hat Kx means that there is someone at X or generation K of my process. But it can be just 0 or 1, or it's occupied or it's not. But the idea is to couple this with the branching random walk envelope. This guy could have many people sitting. It's a critical branching random walk. Okay? So the fact that it's critical suggests that you might use it in order to. So at each time, occupied sites in this one, they branch according to a binomial. There are 2n, probability 1 over 2n, and move to one of these 2n neighbors uniformly. And this is done everywhere on Z. But you start from the origin, so you keep going. You keep growing this cluster of the origin. Okay. So for this envelope, it's clear that you, when you do some scaling limit, you should have a diffusion because it's a critical branching random walk. And this diffusion scaling limit is simply Dawson-Watanabe process. It's given by an SPD. And now you need to understand the proper attrition for the other one. No? That there are some, you can have only one guy sitting at a place, and you cannot, a place which has been already been visited cannot be visited again. It doesn't count. Okay? So this is what we call it the attrition. No? And to understand the scaling limit of the true process. So for this part, what inspired us was a work of Steve Lally in 2009, where he studied the scaling limit of discrete SIR epidemics. On the situation he had was this. You have a sequence of torus with n guys, so like he called them villages. In each one can, the reason for 3n, because each one has n guys here, but you can infect someone in your own village or in the neighboring villages. The others you don't have contact. Okay, so he studied this dynamic. So it's the same situation as here, except that the graph is quite different. It has some similarities, but it's a completely different graph. It's a different graph. But the inspiration came. The exponent is different, but the inspiration came. Okay? So in order to do this scaling limit, we want to consider how it behaves the density of my process. So I scale. I want to make the scaling limit of my process. So in order to get a continuum process in the limit, I scale down, of course. Instead of going from 0 to n, I go -1. It stays between -n and n, between -1 and 1. So I scale down space by that. Then I apply a diffusive space-time scale. For the moment, I don't know which alpha will be good, so I take any one. Then afterwards, we'll find out one which is interesting, and that's why the 2/5. Okay? So I take this is my process. This guy represents an approximation for the density. So this guy plays an important role. I want to know what happens with it as n goes to infinity. You know? So for the question which I want to answer, that if there is percolation, I can start with many guys. So I start with something which approximates the identity. So I start with a certain number of particles. They are equally spaced between this guy and this guy. So that means in my notation, I start with some approximation of -1, 1. And I want to see how this evolves for this evolution here. Okay? So this is our goal. So the envelope process, which is just the branching random walk, a critical branching random walk, is very simple. No? You can construct it immediately like that. This represents the generations. No? So I start Cn at x will be obtained by, at each time you have each particle branches according to a binomial, 2n, 1 over 2n, and then chooses where to go, uniformly among the 2n neighbors. This is just the branching random walk. So this I can construct like that, very trivial, very simple. These guys are Bernoulli, independent, with parameter 1 over 2n. And this is my approximate density. So for this process, you have no doubts that it should converge to a diffusion. And since you can prove that this converges in law to the Dawson-Watanabe diffusion, which is the unique solution of this SPD, which is here. So though this should be a theorem written in several places, in several papers, because it's a kind of a classical stuff, we gave the proof. But the proof, and it's simple how to understand why it should be, because you just write down a discrete version here of your equation. This is just how Cn evolves. Now you remember Cn is this, and then you write what is Cn. Just subtract and add something. This is the same expression which I had there. And you see, out of here, you see this comes a space-time white noise, and out of C, here you see the Laplacian. So it's a matter of proving that you have tightness, and the martingale problem has a unique solution. And this can be done, no surprise. And this is similar. This proof is similar to work done by Carl Miller and Roger Tribe, where they studied another particle system. I think it was the Voter model. Okay. So you know something about the random walk envelope, the branching envelope, but not about your process. So you need to control the attrition, no? Because you need to know what you are going to lose, because you cannot visit a place which had been visited before. So you need to count this properly in order to find out which alpha gives you the right behavior. In order to do that, first you look at the total mass of the envelope process, and you can prove that this guy behaves like that. So it's a diffusion which you can describe very properly. This is the envelope. But just because you need to control what's the probability to have an upper bound for the true process. So you need the envelope. So this is, I mean, it's not difficult to get this, but one needs to do, but I guess you believe out of that equation that you have that. And from this you can prove, from this equation, you can prove that this stays finite, total mass stays finite. It's, I don't want to give the details now because otherwise I am lost in time, but it's not difficult to get this. And using this, you can prove that the probability of multiple, at least two particles in the same size is very small if alpha is less than 1. For any alpha less than 1. For the moment, you can see that. So you get also for the envelope, for the other process, because you can couple C hat, so that is below C all the time. Okay, so that's what we know for the moment. For the moment.
You always are criticality.
Yeah?
The branching process is always critical.
Yeah, it's always critical. Yeah, always critical. So now I go for the horizontal process, and you make the construction of the horizontal process coupled with the other one. No, because what it is, the horizontal process, I need, my Bernoulli needs to, from one of the neighbors, need to choose one of those guys to be, and the guy couldn't be occupied before, because you cannot visit a site which was had already been visited, because it's the percolation. So C hat of X is going to be 1 only if there is someone here. So this is coupling with the other thing, and this guy was not visited before. Otherwise, it's 0. So you can make, you can write your C hat at time k plus 1 in terms of the etas that you had for the other process times this and a small error. This can be treated as an error because we can prove that it goes to 0. So this allows us to put a handle on the true process out of this equation. And out of this, we can prove that if you take alpha equal to 1/5, now I say why, 1/5, then this guy converges, the approximate density converges in law to U hat, which is the unique solution of this equation here. And this equation is simple to understand why, because this is the attrition. You cannot be occupied before, because if a site had been already visited, it cannot be visited again. It doesn't count. So it is clearly why this, I mean, it's natural. Then, of course, one needs to prove. But the proof involves making all figures. But it's natural to understand why you expect something like that. No? In the other one, you had U. And why alpha 1/5? Well, because we started with N2 alpha particles in N2 alpha plus 1 vertices. That was how we started with. Maybe I have to show again, but it was already here. We started like that, okay? Because that's the approximation of the 1. Like I want to start with something which is 1, the density. In my equation, 1 is the initial condition. So we have N alpha minus 1 per site, particles per site. This random walk, branching random walk is critical. So it keeps like that while alive. It lives for N2 alpha. So you can think the following. Whenever you can make the construction of this hat on the top of the other, say, I have two types of particles, say, blue and red. The blue are those that don't count, are that. So when it comes, the children of a blue is a blue. And if it comes to a place where it has been visited, it becomes a red puts a child on a place which has been visited, it becomes blue. So if you count that, the attrition which you get will be for each particle will be, since it lives over to alpha, and then n alpha minus 1 is the N3 alpha, this times what I'm saying, N alpha, because I'm writing wrong, of course. This one is what you lose, because this is what you have. If it comes to a place which is occupied, it becomes blue. So this guy dies. For each particle, you have this total attrition in its lifetime, but there are N2 alpha. So you get N5 alpha minus 1. So the N5 alpha minus 1 being critical, that's when it changes from being going to 0 to being going to infinity, is alpha 1/5. So that's how we guess that it should be 1/5. And that one is to prove then with 1/5 it will work. But sometimes these intuitive arguments say we had some arguments but for the Ising it's more involved to have intuitive arguments. For percolation here, because we had the branch, and we end up with the wrong conjecture. Anyway.
One line question. When you so you are trying to do the branching, approximate the on the horizontal line by a branching random walk. Can't you look at like a multi-type branching random walk? Does it give a good?
Well, I don't know if it is. We could think that I have these particles and I color them with two colors. That's like two types, red and the blue. Say red still counts, blue doesn't count anymore. But since I have only two types, then I consider only the ones that are interesting. But it's more or less what you were saying, I think.
Yeah, in some sense.
And what is important is that the ones that I am interested in, they converge to something. This density of particles, this is the approximate density, converges to the solution of this equation.
Okay.
I don't know if it answers what you wanted, but it's... if we had a more involved thing with 3 types, then I would have to look at least 2. But since I have only 2 types, then it's enough. I consider only 1. And what I lose on the way is this attrition. Okay? Okay. Once we prove that, it stays with 1/5, we can get that the expected size of the cluster is L, is bounded by a constant that I don't care, universal constant, n to the 2/5. Because if it's 1/5 and lives by 1/5, then all that the size of the cluster is the total population. C0 is just the cluster of the guy restricted to 1x. So it's the total population of my C process. Okay? And the total population is going to be this size. I don't know, depending on the time, I can give some arguments. How much time I have for the moment? Half an hour, okay. So if time allows, I can come back and tell what it is. But once you prove that, since you see that the density is 2/5, 1/5, then you know that the total size is going to be n to the 2/5. Okay? And once you know that the cluster of the origin, the cluster of restricted to a lane is n to the 2/5, it's trivial to get that if PV is kappa n to the minus 2/5, and this kappa is small, then you cannot percolate. No, just like the same proof that says that P critical is positive, because it cannot grow more than a branching. You can prove that easy, but let me say, we need to believe this one. Okay? This is the important. This comes from this, because this guy converges in law to something. The important that converges in law to something, which is given by this equation. So it stays in this order. So once we have that, so how you get this is trivial, because you can, how you start with 0, then it grows its cluster in here. Okay. Then this guy might, any of these guy might, with some probability, create some family here, but this family is at most n to the 2/5, and so on and so on. So you are comparing this process which you are interested in, which is the cluster of this guy, with a sort of branching process where these guys are binomials with this these variables, and the PV is the same, PV which you started. So each time it has some child, this guy here has a family which is n to the 2/5. Out of each of these, you have n 2/5. So if PV is n minus 2/5 times a small constant, then it is compared with a subcritical branching process. It's the same argument that you use to see that if you look at Bernoulli percolation on the plane, then P critical is positive. If P is less than the branching, you have at most four neighbors to go. You cannot survive because, of course, it's much smaller than the branching process, because afterwards it will come to a place which had been already visited. So here it's exactly the same, and this follows very easily from that one. So you get a C1 which doesn't depend on anything. The other part is more involved. I want to see that for kappa large enough, with a constant that doesn't depend on anything, I'm able to percolate. Now, of course, you need to look in detail of your process. And what we are going to use percolation only upwards, because it's enough. But this is not. So what we are going to do at the end is sort of a block argument, which is kind of very general argument for gross processes. Block argument reducing to, so I will consider like my new something which I didn't tell what it is exactly, but I will have some block which represents some space piece of my environment, and I will tell what does it mean this block to be open, say. Now I have an associated random variable to this block, which is going to be somehow big here. -1, 1 is where I started with particles here, and I want to see there is a positive probability that it stays forever. So I'm going to say, to give you a definition of what does it mean this block to be open, or whatever, the site to be open, and this will be something which must have a very good probability. There is some parameter delta that I invent myself, and I want to be very small, because I want this probability to be very close to 1. This will depend, these things are not going to be independent, but they are going to have they will depend only for the neighbors. So one dependent. If they are more than 2 separate, they are independent. So, and it's a general theorem that if you know that and delta is small enough, then this percolates. Once you are able to prove that this probability is close to 1 as a function of delta. And that's what we need to prove. So in order to prove that, I need to say, first I of course need to tell you what is the kind of thing. So this is just what I was saying. This is a general fact, renormalization, one dependent system with this probability, if this will percolate. So I'm going to say that the interval is good if it is uniformly occupied with a density 1. Do you remember we had proven a theorem that if I start with a density, then it converts to the solution of that equation. And here it comes a problem that was quite an effort to do. So here I tell as if it were trivial, but it was not. The point is that when you want to show this, it was not enough to look at the scale that we were looking. We need to look at, because there was a scale at which we show that this process converts to this solution. We need to look at a more detailed scale, and this was a problem. So we need to look something more detailed and refine the scale, because this power is bigger than 1/5. So and this one works. So, but this required an extra effort in terms of the continuum limit than just the, what we had in that theorem. Maybe there is a way to do something more universal, but we don't know. So we need to, what we can do with this is that if, I will say that an interval is good for these scales if I have no empty, you know, I have any interval of this size, will have people, but not outside. So I want to say that I have a very good approximation of the identity in this interval. And why I want to control the outside is because I want to disregard children which are too far. And why I want to disregard them? Because I need to have one dependent. I cannot go too far. In order to use more general argument of Kessen for branching random walk, we needed that. Okay, and by doing that, we can prove this, that if initially you have this interval, which is good at this scale, then with large probability, that means neglecting something delta to some power, we are going to have a little bit bigger interval, a little bit bigger, you see there is this 2/5, which is going to have a good density of people. This A was approximate density all the times. Okay, that means that I am able to grow this here. This was good here. I let it will be good in a little bit bigger. So after a certain number of steps, I have it bigger enough. That's just computation. Oops. And with that, we can prove that if you have it, you have this guy grows, it's given by this first proposition, and grows enough, and then with large probability you find one vertical connection, because you need to go upstairs. Once you go upstairs, you grow again, and you need to find this upstairs with good probability. Everything has to be good with a probability which goes to 1 in delta. So we have this other proposition. If this guy is good, good means what I said before, then you have a good in a little bit bigger, and there is one guy here which is going to be open for all this on the top, and this edge being open. So it creates this cluster on the line above. So in this sense, you can prove if omega mn is good, omega n is good means that I have it, this guy good at that occasion, then this guy is going to be good in all this in all this box. I'm going to be able to prove that this will have a very good probability, because I just said the following. I messed up here notation. I need to refine. I need to say an interval is good if in this scale I have a good number of particles, neglecting what is outside. So I put outside is 0. Okay? And we are going to that's why I put a tilde here in the process. I'm sorry that I didn't say. I kill what is too far away. This is to control the dependence. And then you need these two propositions, which are not too hard to prove, but involve quite a bit of computation, of work, But it's more or less in the same spirit as the theorem of the scaling limit, that if you have a good interval here, then with large probability, close to 1, you have it a bit bigger interval for all this case, and moreover, even neglecting everything outside, you find one guy which is open, connecting family downstairs with family upstairs. And once you do that, it's you are in shape to use the kind of one-step renormalization. So you set this guy to be good if this occurs, what you just said before, no? Which is it stays growing, and it has dot picture, which I said there. And then you are going to say that an edge is good if both sides are good. That's a trivial general scheme. No? I'm going to say that the edge is open if both renormalized sides are open, similarly for this one, but then the probability is good. And you can prove that proves the theorem in a general way, no? Because this is a general argument. This is very general. Once you have a one-dependent system with probability 1 over delta, delta small, no, for delta small, then this percolates with positive probability. And so there was a technical work here, because if we could be comfortably sitting in 1/5, then it would be easier, but we couldn't. We had to go to this more refined scale in order to be able to grow properly and to find the connection. So I think it's we don't know how to do for the Ising. Here are the references. So this is basically on this paper, which was with Tom Mumford and Hal Schur, who was at that time a student of Tom. And this is the tribe Miller. So I can give detail more if you wish. Thank you.
Questions?
I just want to understand this 1/5 again. So this calculation again. So, so what's the n to the alpha minus 1 is the number of spacings, right? Or
The number of particles.
which is
For each particle, it stays n to the 2 alpha,
very good.
and at each the attrition it feels, because when it meets someone that was occupied, site that was occupied, it doesn't count, and the occupied is alpha minus 1.
So that's
So
the spacing,
n
is
to
it?
alpha to alpha minus 1. This for each particle, all generations.
How do you
And
get
this
n to
is
the
for
alpha
the
minus
number
1?
of particles.
How do you get n to the alpha minus 1? Is it because the spacing is n to the 1 minus alpha?
Yeah,
Is it-
because I had 2 alpha particles and 2 these sites. This could be, in principle, could be general, but that's the way we have to. Because to make an approximation of 1.
Any other questions? Okay. If not, let's thank Maria.
Thank you.